Dear students, let's continue where we left off yesterday. So we're looking at analysis of steady state error. And we've covered all these fundamentals, all the derivations for the steady state error from the closed loop transfer function, from the forward transfer function as well. So now we are using the term we obtained for the forward transfer function, G of S, in a block diagram like this. Yep. So this is what we're using mostly, but we've also seen if we had, of course, the closed loop transfer function, we can, of course, still find the steady state error. So look at that. Now we stopped last time on an example with work examples. This is what we've covered already, where we found the steady state error for step input of magnitude 5, a ramp of magnitude 5 again, and parabolic input of magnitude 5. So we've derived, we've applied the findings we've obtained for the steady state error with step, yep, then with ramp, and then with parabola. So we ended here. So let's look at the second example now. If you had a system like this, so just by looking at the block diagram here, we find it's a type 1 system because we have S power 1 here, and it's a unity feedback system. So all the equations we've derived here now are still applicable. Now, if you have a type 1 system, yep, we expect type 1 system should be able to track position with 0 error, should be able to track constant velocity with a non-zero steady state error, but yet not infinity, but it will not be able to track a constant acceleration body. This is what we found last time. So let's validate that using calculations now. So we've seen if we want to find a steady state error for step, this was the expression we got, and of course 5 appears here again because it was 1 here when you were studying a unit step. Now it's a step of 5. So like we said earlier, if you find this limit as S tends to 0 of G of S here, so you have a 0 here. So this 0 is going to put an infinity, so where the infinity is coming from. So 5 now over this limit here, we get 0. So like we said, first, a type 1 system should be able to track position. Now, if we find a steady state error for ramp, so this expression here, we again have 1 here for unit step, but for a ramp of magnitude 5 here, we have 5 here, over limit as S tends to 0 of SGS. If you find this limit here, this S is going to cancel out with this limit here. And then in the, what remains is, of course, when you replace S by 0, you get 100 times 2 times 6. And then in the denominator, S, of course, is cancelling out. This S here, then we have 3 times 4, so this is 12, 12, you get 100. So this is what is 5 or 100, so we get 1 over 20. So like we said at the start of this problem, we a type 1 system should be able to track constant velocity system, but with a non-zero error. And here we find the error to be 1 over 20. Now, for a parabolic input, we know this is constant acceleration. If we try to do the same thing here, we get 10. The 10 here again is coming from the expression for parabolic is half of t squared. So this is where the 5 is coming here. And then we find, so it's 10 over limit as S tends to 0 of S squared GS. Okay. And so if you find this limit here, S squared GS, so we have an S coming here in the numerator, which is going to lead to 0. Of course, S squared and then S here, S cancels out, of an S left in the numerator. This is what gives 0, and then 10 over 0 is giving infinity. So this is clearly showing here our type 1 system cannot track a parabolic input, means cannot track a constant acceleration body. So this example here for self-practice, let's just read it out and give you some hints how you go about solving this one. The unity feedback system. So again, so it's a feedback path with h equal to 1 here. So you can apply the equations we did already. Has the following forward transfer function. So it's your G. Find a steady state error for the following inputs. So you're given here a step of magnitude 15, a ramp of magnitude 15, and a parabolic input of magnitude 15 again. So what we expect to get here is type 1 system. So when you apply the step, the error should be 0. When you apply the ramp, the error should be constant, and when you apply the parabolic input, the error should be infinity. Now, if you repeat for part B here, we find now we have a type 2 system. So a type 2 system should be able to track position without any problem, should be able to track velocity without any problem. And when you try to track now acceleration, constant acceleration, you will get a constant error. So just validate that and just find answers. So you can apply very similar type of equations we had for the work example. So this is an opportunity for you to try it and to approximate. Now, if you just review now, so let's move on now to another topic in the same chapter now called steady state error constants. Nothing new we are doing now based on the expressions we've derived already. We're just going to simply define a few terms which are known as steady state error constants. So these are the three expressions we've got here now for the steady state error for step was 1/1 plus limit as s tends to 0 of g of s. The steady state error for ramp input was 1 over limit as s tends to 0 of sgs, and the steady state error for parabolic input was 1 over limit as s tends to 0 of s squared g of s. Okay, so what we're simply doing now, we're simply naming these limits here, the three limits we have by a constant, and we are calling them static error constants. So we know when the first expression here, when we are dealing with step as position, so we're going to call this limit here kp, the p stands for position. And when we had the expression for the ramp, we had 1 over limit as s tends to 0 of sg of s, and then we're simply replacing this expression here by kv, v for velocity. And in the expression for the parabolic input, we had 1 over limit as s tends to 0 of s squared gs. So we are simply replacing now this limit by ka, a for acceleration. So if you are asked to find the static error constant for step input, it's kp, you have to find this limit. If you ask to find the static error constant for ramp input velocity, so you have to find this limit. And similarly, if you want to find the static error constant for a parabolic input, which of course relates to acceleration, you're going to find this limit. As simple as that. This is how it translates everything. So it's a position constant, the velocity constant, and acceleration constant. So nothing new as such. It's very similar expression we've been working with, but now you could of course find kp first, and then just plug kp here. You could find kv use this expression, and then replace kv here to get your steady state error, and simply find k here for your parabolic input, and just replace it here to get your steady state error. So we saw some examples now for us to practice a bit on the static error constants. And once, of course, we find the static error constant, you can of course find the steady state error corresponds to these three inputs. We know step with kp, k ramp kv, and parabolic inputs going to be k. So if you take the first one here, which is a type 0 system. So for type 0 system, in a type 0 system, you expect to get an error, steady state error, which is constant for position, but for velocity, expect to get infinity, means cannot track, and for acceleration, same thing. So if you're getting here a steady state error which is constant, it means your kp will be constant here. Okay, your kv would be 0, and your ka will be 0. These errors. So when we actually deal with this one here, this one is a type 1 system. So for type 1 system, we know it can track position, it can track velocity with a non-zero error, and it cannot track acceleration. It means when you want to find kp here, you will have infinity. When you want to find kv here, you get a constant, and when you find ka here, you're going to get 0. So let's say that to be infinity. Now, if you have a type 2 system, where a type 2 system can track position, can track velocity with 0 steady state errors. It can track a constant acceleration body, but with a non-zero steady state error. So from there, you can infer that your kp will be infinity, your kv will be infinity, but here your k will be constant. So you get 1 over k will be constant, a non-zero steady state error. So let's try it now and test it. So this is the first one. If I just go one slide back, so we're looking at this one here, a type 0 system. So kp is limit as s tends to 0 of g of s. So just find this out, and as we've said earlier, you would get a constant, and plus kv and ka would be 0. So if you want to find the error now for a step input, it's going to be 1 over 1 plus kp. If you want to find the error for a ramp input, it's going to be 1 over kv simply, there's no 1 plus there. And for ka, you would get 1 over ka. So this is what we do next. So once you found kp, you just replace the value you've got here, you replace in this expression, you get your steady state error. And for ramp, you get 1 over 0, and for parabolic input, 1 over 0, again infinity. So this is consolidating what we said earlier about a type 0 system. A type 0 system can track position, but with a non-zero steady state error, it cannot track velocity, cannot track acceleration. Now, the second part here, type 1 system. Okay. So if you find your KP here, limit as s tends to 0 of g of s. So this 0 here not be cancelled out by anything because there's no s in front for KP. So this 0 here is going to lead to infinity. KV, of course, is SGS. It's going to cancel out this S here. When you replace back, you're going to get these terms here, 31.25, whereas your K is S squared. So only 1 over S will cancel out, the one S only on top, so you get a 0 here. And similarly, you can find now your steady state error for the free inputs. So we've got KP here infinity, so 1 over 1 plus infinity is 0. For wrap input, 1 over KV, so you get a constant. And for parabolic input, you get 1 over 0, you get infinity. So this reinforces again what we said about the type 1 system, being able to track position, being able to track velocity with a constant error, non-zero steady state error, and cannot track acceleration. Third control system in the same question we're dealing with about C here. So type 2 systems, the type 2 system can track position, can track velocity, can track acceleration, but a non-zero steady state error. So KP limit as s tends to 0 of g of s. So this s squared here is not cancelled by anything. There's no s here. So if all these terms, of course, is going to be constant, and then you have a 0 in the denominator, which gives infinity. KV is s here, so only one of the one s is cancelled out here. So you have an s remaining in the denominator. We replace it by 0, you get infinity. And KE now, you get s squared gs. So if you have an s on top here, it's going to cancel out this one, and then you get your constant. So you get a constant term here. So from here, of course, you can find a steady state error. So 1 over 1 plus KP gets 0. With wrap input, 1 over infinity again gets 0. But for parabolic input, you get a constant, a non-zero steady state error. Again, you can make the same inferences we've said about the type 2 system. Is ability to track position, to track velocity, to track acceleration as well, but was the latter one with a non-zero steady state error. So this table here summarizes very well what we've just done as a summary about type 0 system, type 1 system, type 2 system. These are the, of course, for step, the corresponding constant, called position constant, velocity constant, and acceleration constant. So these things, and how you calculate your steady state error from the static error constants is 1 over 1 plus KP here. So you have to remember for position is 1 plus here, and then for a wrap and parabolic is just 1 over the static error constant. So if a type 0 system, we've said it is able to track position but non-zero steady state error. So your KP will be constant, whereas these two would be 0, means your error will be infinity, cannot track. A type 1 system can track position. This is why KP is infinity to give a 0 error, steady state error. It can track velocity, but the non-zero steady state error. This is why this KV is a constant here, and then of course 1 over KV. It cannot track acceleration. This is why your Ka is 0, so that when you take 1 over K, you get infinity. Type 2 system can track position, can track velocity, can track acceleration with a constant steady state error. So your Ka will be constant, but here Kp infinity and this one infinity. So ultimately you get an error for the step input of 0, an error for the wrap input of 0, and for the parabolic input you get 1 by k. So a constant is, of course, you could build on that in type 3, type 4, and so on, and get corresponding deductions. Yeah. So self-practice example again, let's just discuss that. So a unity feedback system has a following forward transfer function. So a type 0 system. Yep. So you want to evaluate system type first, and then KP, KV, and K. So you should be able to do that. And use your answers to A to find the steady state errors for the standard step, ramp, and parabolic input. So you should be able to do that, especially based on this table here. You have all your answers here, so it's good chance for you to practice. Okay. Now, why we studied that? When we started this presentation on steady state error analysis, we mentioned we are studying steady state error as a means to set specifications for control systems. Yeah, we have said we can set specification based on transient response, on stability, and also on steady state errors. So how would we set the specifications of a system in terms of steady state response? We can do that using the static error constant we've just studied. So for example, here, if a control system has specification as follows, so you want to have a KV of 1000, what can be inferred from it? So if you have a KV of 1000, first thing It means you're dealing with what type of input? You're dealing with ramp input, because a KV is defined for ramp input means the constant velocity object that you can track. That's the first thing. The second thing you can infer from there, the moment you do that, is you can find the steady state error. It's always 1 over KV. What can you say about the type of system? So what type of system has a constant steady state error for velocity, for tracking velocity? Yep, so this is what we've been saying. So the system is stable first. If you're getting a steady state error, if you have a KV, the system is stable. The system should be type 1, because it's a type 1 system that has a constant non-zero steady state error for tracking a constant velocity system. Yep. So if you recall here, KV will be 0 here for type 0 systems, whereas KV is infinity for type 2 systems. In that table here we've seen earlier. So we are saying here your KV is constant and your KV is constant for type 1 system. So just by putting the specifications here, KV is 1000, you know it's a type 1 system. So lots of information hidden here. Like we said, a ramp input is a test signal. Yeah, this KV is defined for a ramp signal for tracking the constant velocity system, and you can of course work out a steady state error from there as 1 over KV. There's lots of information hidden there. So similarly, what information, as a work example, what information is contained in the specification? KP is 1000 now, so we're talking about KP. So you need the decimal step now, and since KP is a constant, so for what type of system is the steady state error constant? Is it type 0 system? So first, the system is stable, that's fine. The system type is 0. Since only type 0 system would have a finite KP, means a non-zero steady state error. Now we see that, and the input test signal is a step. This is KP. And finally, you can find the steady state error. It's 1 over 1 plus KP now, so you can define the steady state error as well. So clearly, we can set specifications for control system using static error constants. This is where we're coming up with this. So this is one example for self-practice. So just look at it. Given the control system, you find the value of K so that there is a 10% error in the steady state. Okay. So once you get the value of K there, you can of course check if your system is stable or not using the Rath-Hurwitz criterion. So how would you do that? I leave it to you just to take on board all the various principles we discussed now about seeing a 10% error in the steady state. So it means your error should be 1. If you have a 10% error in the steady state, so if it's a type 1 system, what are we talking here? What type of error constant we talk about? And so on. So try to think about this. Second self-practice example here. Okay, so unity feedback system has a following forward transfer function. Find the value of K to yield a 10% error in the steady state. So this example, the previous self-practice example was a type 1 system. This one is a type 0 system. So again, it's up to you to find what type of system, what type of error constant rather, what type of static error constant would be relevant here for a type 0 system to have a constant error. First thing, it's 10% error in the steady state. It means the error will be constant. So again, these two examples are related. Okay, now to finish off this chapter, last topic is left in what if the feedback path we have been using till now. So this feedback path here is not unity. So it's not a unity feedback system. So you have an edge here. What happens? Now, very important to understand the implication of putting an edge here is always your error is defined as the difference between your input and your output. So if you were to put an edge here, as follows, if you put an edge here, now the error you're getting is R minus CH. So that error, which is actual error, EA, is not the error which we want, because we want to get an error which is R minus C. Means you would need to make changes to the block diagram so that you bring this back to unity feedback system. So how can this be done? Let's look at the steps. So this is what we have currently. Yep. So again, we have an EA here, which is R minus CH, which is not our error metric. So first step we do here, we want to have a feedback system here. Yep, so you want to have this unity feedback system. So if you put that, you need to put a -1 just to compensate. So this -1 here. So you're subtracting 1 here. Your, of course, again is 1. You're subtracting 1, then you need to add 1. So you're minus, you're adding 1. So this is leaving the same result. But interestingly, first, we are having this feedback path. Of course, second, we need to add this to compensate. Next, what can we do? So this is a block diagram we are now. So the change we're doing now, we can lump these two together. So these two are being subtracted. So we can subtract here h -1. Now from here onwards, what can you do? You can, we know when you have a node with 3 inputs here, we can just split this node into 2 nodes, this plus minus this one, and then again plus the result of this minus this one. So you could apply now the closed loop form, the rule we have discussed when we're discussing the chapter on block diagram representation. Use g over 1 plus g. So your g is g here, and your h is hs minus 1. So this is what we have. If you apply this closed loop form here, you will get this one. So it's g over 1 plus gh. So your g is 5, and it's 1 plus g times h minus 1. So it's gh minus g, what you get. So when you have a block diagram of this form, you would have to make this change. You get a unity feedback system, and once you have this one, you're getting now your ES. This is very important for us because ES again is R minus C. So once you do this compensation, the system, you bring it to this form, then you can apply the all levers principles we've discussed already. Let's look at one example. So the system shown below, find the system type, the appropriate error constant associated with the system type, and a steady state error for unit step input. Assume input and output units are the same. So here I'm saying R and C have the same units. So again, you can see here, if you are in this configuration here with a non-unity feedback, you would actually have an actual error signal EA. It's not the error we want. You need to apply this compensation. We have here G over 1 plus GH minus G. Okay. Now be very careful about when we talk of system type here. The system type is not 1. The system type is not 1. You would have to apply this compensation, and from the results you obtain, you will be able to comment on the system types. You see, this works out. So in this case, your G is 100 over S into S plus 10. So this one, and your H is non-negative, is not 1, is 1 of S plus 1. So we find this equivalent transfer function compensates as G over 1 plus GS minus G. So if you do that computation using G and H here, you get this result. So you can clearly see now the system type is not 1, it is actually 0 because there's no integrating term common outside. Okay, there are no pure integrations. Appropriate static error constant to use in this case is AP. That's a type 0 system, and you find, of course, when you find KP limit as S tends to 0 of GES, of course, KP, you're going to use KP now. For type 0 system, the appropriate error constant to use is, we're talking here of a unit step input. This is why you're using KP. Type is 0, and for type 0 system, unit step, we know we get KP constant. So of course, once you get KP constant, you get the value of KP, you can just work out the steady state error. So this very well illustrates what you need to do when you get a non-unity feedback system. You have to make this change first. If you don't do this change here, the result you get will not be correct because you'd be solving for the EA. You'll be finding the steady state value for EA, not for the error, which is R minus C. Now, self-practice questions. So if I find a steady state error as follows, R minus C. For unit step input given the non-unity feedback system. So again, you have an H here which is not equal to 1, so you would have to compensate. So once you do that, you can repeat for unit rep input, assume input and output have the same unit. So once you work out, you can do that. Now part B here, find the steady state actuating signal, EA. So you want to find EA now for unit step input given the non-unity feedback system, repeat for. So to be able to solve part B now, we don't need to make the compensation because we want to find the steady state value of the actuating signal EA, the actual error. Part B is more here. You will need to find an expression for EAS and then follow the same steps you have covered earlier to find the steady state value. Remember when you are able to find right at the start of this chapter, the first step you have to do to be able to solve a steady state error for the error was to find expression for. So similarly here, you have to find expression for EA. in terms of R, and the other terms here like C. So you'll be able to solve that first. Once you get the term for EA, it's just a question of applying the final value theorem and getting the answer. Of course, your EA will be in terms of R. So the first step, you would replace that R by 1 over S for unit step. And in the second time, you will replace it by 1 over S squared for unit ramp. So that's it for this chapter on steady state error. I hope it has given a very firm grounding to you. A reference for the material I have been used is Norman Nees. Yep, Norman Nees, a control system engineering, 6th edition. So this has been the reference that I've used in this presentation. Thank you very much for attention. And I'll be coming forward, of course, with other videos on content engineering. Thank you.